AP Cactus AB, Unit 6, Day 16 lesson. It's our last new item of Unit 6. So inverse trig derivatives. So we're going to add, this will be the last derivative rules I teach you for the whole year. Before we get into the derivatives, let's just review what inverse trig functions are, what they look like. So you have a little subscript -1. So these are inverse functions of the regular trig graphs. And sometimes they call them arc sine. That means the same thing. So let's do what we've done with other inverse functions and start with the original graph. Let's graph the sine curve first. So the sine curve, kind of looks, let's see. It's 2 pi. We'll graph it over here too. So we're just going to start with the sine curve. The sine curve, messed up. Okay, sine curve looks like this. Right? So we're going to flip it across y equals x like we've done for other inverse functions, but we might try and get some of these points down. So pi 0 becomes 0 pi. So that's going to be up here. The x-intercept becomes y-intercept, right? And negative pi 0 becomes 0 negative pi. So that's down here. And there's going to be dots here. And the range of the original graph is going to become the domain. So it's only going to go between 1 and -1. So if we flip it, it looks kind of like this. And it keeps going forever. It's up and down. Now, the problem with this, that inverse sine graph, it's not a function. It fails the vertical line test. So what we're going to do is we're going to restrict it to just a portion of that graph so that it is a function. And we're going to pick the piece of the graph that's as close to the origin as possible. So, I mean, you could break it up in a lot of different ways, but this is the piece of the graph that everyone agrees is inverse sine. And the angles that create this, this goes from negative pi over 2 to positive pi over 2. Those angles represented on this graph, the output, are called the principal values of inverse sine. And so the principal values are the angles that you get from it, negative pi over 2 to positive pi over 2. These are the values you get on your calculator when you use inverse sine. The domain is now -1 to 1 because it was the range of the original graph. So this is these principal values right here are one of the things that you need to remember. So in general, what they are is they always involve quadrant 1. All of these inverse functions, principal values, will involve quadrant 1, and then a quadrant next to quadrant 1, either quadrant 2 or quadrant 4 backwards. But it's got to be in such a way that quadrant 1 is always going to give you the positive values of sine, cosine, tangent. And so you need one that's going to give you negative values. Quadrant 2 here is still going to be positive. So that's why we're going to use quadrant 4 and not quadrant 2. Because it's a function, so you got to have every input has exactly one output. So that's inverse sine. Inverse cosine is similar to that. Let's jump to inverse tangent, arctangent. So we're going to start with the graph of tangent. Now, the graph of tangent is sine over cosine. So when I'm trying to graph tangent, or even arctangent. I'll start with tangent, but when I'm trying to graph tangent, I think of sine over cosine. So whenever sine is 0, you're going to get a 0. Okay, so you get 0 there, you get 0 at pi, you get 0 at 2 pi, right? At negative pi, negative 2 pi. So whenever sine is 0, whenever sine has an x-intercept, tangent has an x-intercept. Whenever cosine is 0, pi over 2, you're going to get a vertical asymptote. And 3 pi over 2. And negative pi over 2. And negative 3 pi over 2. You can get vertical asymptotes. And then the graphs kind of go like this. Cotangents kind of like this. One of them goes like this, down left to right. One goes up to left to right. All you got to think about is quadrant 1, sine's positive, cosine's positive. It's going to be positive, and it goes towards this vertical asymptote. Right? And then it repeats itself over and over again. The period of tangent and cotangent is just pi. And you can see it here. It repeats itself every pi. Now, what we want to do is we want to flip this across y equals x. So one of the first things I would do is I would flip the vertical asymptotes into horizontal asymptotes. So if we're going to get a horizontal asymptote at pi over 2 and negative pi over 2, and then you're going to get more at, 3 pi over 2, negative 3 pi over 2, and then keep going forever. So when we flip this, it looks like this. So we get a bunch of these. It looks sideways. The inverse functions are always going to look sideways versions of the original. Now, again, this isn't a function because it fails the vertical line test. So we're going to just pick a part of it, the part that's closest to the origin, to be our function and restrict the values we use so that it is actually a function. So this is the portion of the graph that we use for inverse tangent. So the domain is going to be, the domain of this one is going to be negative pi over 2 to pi over 2. Actually, no, the domain is going to be all reals. Domain goes forever left and right. It's the range that's going to be negative pi over 2 to pi over 2. And the domain is all reals, negative infinity, positive infinity. Now, we don't do the order equals to here because those are asymptotes, so we never actually get to those values. But again, this is quadrant 1, and this is quadrant 4 backwards. So principal values for inverse tangent are quadrant 1 and quadrant 4, but backwards. For cosine, if we were to look real quick, the cosine curve, see if we can just do it real quick. Flip it across y equals x. It's going to look like that. And so we want quadrant 1, but if we pick quadrant 4, it's going to be also positive and positive, so we pick quadrant 2, which ends up here. So the domain is negative 1 to 1, just like it is for inverse sine. The range is 0 to pi, which is quadrant 1 and quadrant 2. That's for inverse cosine. Okay, so that was a quick review of these. Some other interesting things we could ask ourselves: what's the limit of inverse trig? Now, it's only when inverse trig is already there that we restrict it to principal values. If you introduce inverse trig, then we're looking at the infinite values. But just itself as a function given to you with inverse tangent already there, then we restrict the values. As x goes to infinity, what does the graph of inverse tangent go towards? It goes towards pi over 2. How about if you're going to negative infinity? It goes to negative pi over 2, right? How about Here's another one. How about the limit as x goes to infinity of the derivative of inverse tangent? Think about what are the slopes doing as you go to infinity. Well, if it's going towards a horizontal asymptote, that means the line is getting flatter, 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 flatter. The slopes are going to 0, right? Okay, by the way, on a graphing calculator, if you were to graph inverse sine, it would actually only graph this portion of the graph. Like I could show you real quick from -1 to 1 and -pi/2 to pi/2. That's the only part of the graph that it would actually display. So let me show you real quick. So if we do inverse sine of x, go to window, we could say, I don't know, -5 to 5, -5 to 5. Graph it, and look, right there, it just stops. So we could get even closer, -1.5 to 1.5, -2 to 2. It just graphs that one part of the sideways sine curve and then just stops. So, okay. Now we use inverse trig. Finding inverse trig is asking you what's the angle, right? This is the same thing as saying sine theta equals 1/2, right? Because technically, if you want to solve for theta, you're going to take the inverse sine of both sides to get rid of the sine and just leave theta, right? Inverse sine undoes the sine. We usually just do that in our head, but this is what it's asking. So you say, okay, well, what's alpha? Alpha is 1 to sine equal 1/2 pi/6. What quadrants? 1 and 2. Now here's the deal. We should only get one answer from inverse trig. One answer, because it's a function. It always involves quadrant 1. So it's definitely going to be pi/6 this time. Okay. How about inverse sine of -1/2? Again, reference angles pi/6. Ignore the negative. It's going to be quadrants 3 and 4. Okay. And so it's got to be quadrant 1 and a quadrant next to quadrant 1, which will never be quadrant 3. So none of these have quadrant 3 as their principal values, but it's got to be quadrant 4. Now be careful. Some people would say, okay, well, that's going to be 11 pi/6. No. You got to go in quadrant 4 backwards. It's going to be negative pi/6. Try it on your calculator. You'll get a negative angle for that. So, anyways, this is the same as that, just backwards. Okay, now let's see if we can talk about the derivatives of these. We're going to develop them, but then you're just going to memorize them because the derivation is a bit involved. So this will be something that we do memorize. So let's start with sine, and let's do it. Let's kind of do it the old school way, maybe, sort of the hybrid way. So if you want to find the inverse, you swap x and y, right? And so this is your inverse graph right here. And if you were to solve, you would say, okay, well, if I'm trying to get y by itself, I got to take the inverse sine on both sides. So that's what we're trying to do. But let's go with this and use implicit differentiation. Okay, so the derivative. So we're going to do this, right? And this is our inverse function, right? The new y is the inverse. So if we take derivative of x, it's going to be 1. And if we take derivative of sine, it's going to be cosine with our inverse function inside. And then you got to multiply by the derivative of what's inside, which is the inverse function y. This is what we want to get. Okay? So if we solve for it, we get inverse, the derivative of the inverse is going to be 1 over cosine of the new inverse y. So this is the derivative of the inverse sine. Problem is it's written in terms of y. So we usually like our derivatives to be written in terms of x, right? So I could draw a little picture of you up here to kind of help you figure out how to rewrite cosine y in terms of x. So if we draw a triangle here, this is y. That's the angle y. That's the new angle y. Sine is opposite over hypotenuse. So this would have to be x. This is the opposite side. And the hypotenuse would have to be 1. Now, we could get a negative answer. X could be negative, and so that would be down here. So principal values are quadrant 1 and quadrant 4 for sine. So here x could be opposite, and the hypotenuse is still 1. Hypotenuse is always positive. And this is the adjacent side. Now, if we wanted to do cosine of this angle, then cosine of this angle would be adjacent over hypotenuse. So let's figure out what the adjacent side is. So that's Pythagorean theorem. I'm going to call it A. A squared plus x squared equals 1 squared, right? Pythagorean theorem. And we want to solve for A. So A squared equals 1 minus x squared. Square root of both sides, plus or minus. It's for sure going to be the positive because this is a positive, side. Quadrant 1 and 4, adjacent side is for sure positive. So A equals the square root of 1 minus x squared. So adjacent is the square root of 1 minus x squared. The hypotenuse is still 1. So the derivative of the inverse of the original function, which was sine, is going to be 1 over 1 minus x squared. So this is the rule. That's the derivative of sine. The so we're going to write a little more officially. The inverse of sine, and it could have some inner function, its derivative is going to be 1 over the square root of 1 minus whatever's inside squared times the derivative of what's inside. That's that whole chain rule idea. Okay? Now, I'm not going to redo it, but we could very easily use a similar proof to find the derivative of inverse cosine. I'm just going to jump to what it is. And in fact, I think it'll be easy to remember. I'll memorize these together. It is also 1 over the square root of 1 minus u squared du dx with one small difference. And one thing that you should all be expecting to be in this no matter what. Anytime we've done a derivative of anything with trig involving cos something, there's always a negative in the answer. And that is really the only difference. Now, the weird thing about these derivatives of trig is that there isn't any trig in the derivative answer, which is kind of strange. So we're going to memorize those. Let's see if we can develop the derivative for inverse tangent. So original function is y equals tangent. So we're going to start with regular tangent. And then we're going to find the inverse by swapping the x and the y, right? And this is your inverse function now. Now, if we take the derivative of this with respect to x, we get 1. Derivative of tangent is secant squared with the inverse function in it times the derivative of what's inside. We're doing this implicitly. This is what we want, okay? So that means the derivative of the inverse of our original function is going to be 1 over secant squared. Now secant squared is 1 over cosine squared. And since we're dividing by it, we're going to get just cosine squared on the top. Now, for tangent, we said it's got to be in the first quadrant, right? So tangent y equals opposite over adjacent. So the opposite side has to be x. The adjacent side is going to be 1. The angle y is right here. Could also be in quadrant 4. So now if we're doing cosine, cosine is adjacent over hypotenuse. We have the adjacent side, right? We have the adjacent side. We need the hypotenuse. I'm going to call it h. So we got to do a little Pythagorean theorem. X squared plus 1 squared equals h squared. So h squared equals x squared plus 1. Square root of both sides, plus or minus. Now, a hypotenuse is always positive, so we're going to ignore the minus option. So the adjacent side is 1. The hypotenuse is the square root of x squared plus 1. So if you were to kind of write this a little more generically, as if there might be an inner function sometime, it's going to be 1 over the square root of what's inside squared plus 1, and then, of course, times the derivative of what's inside, if it's more complicated, which it usually will be. And that's the derivative of inverse tangent. So I developed these derivatives for you based off our knowledge of other derivatives and using implicit and things like that. But we're just going to memorize them. So we're going to add them to our list. Okay. Now, just as one example, something that could be like on your final using one of these problems, find the equation of the tangent line. Now, finding the equation of the tangent line is an age-old question in our class. You need two things. You need a point, right? And so we're going to plug 1 in to our function. So that's going to be inverse tangent of 1. Now remember, this is asking you tangent of what angle equals 1. So you think, well, let's make it a fraction and think of it as sine over cosine. What angle with sine over cosine, the same angle, give you 1 or 1 over 1? There's one angle where they both give you the same value. It's root 2 over 2. It's at pi over 4. It's in quadrant 1 where they're both positive, or quadrant 3 where they're both negative. Now, principal values, because this problem originally had an inverse function, we got to go with principal values. So we're just going to do pi over 4, right? So this is our answer. So the point on our graph is when you plug x equals 1 in, you get pi over 4 out. So that's your point. We need the slope, okay? So the point comes from the original function. The slope comes from the derivative. So this is where our new rule comes in. The derivative, y prime, equals 1 over the, yeah, I think I actually made a mistake here. There shouldn't be a square root, I think. Oh, because this was squared, right? So it should be squared. And so there is no square root. My mistake. Sorry. Forgot the squared. So it's going to be 1 over what's inside squared plus 1. That's where the u thing comes in. Okay, if it's a more complicated expression, it's whatever's inside squared. And then, of course, the chain rule says you got to multiply by the derivative of what's inside. And so we get 2x over x to the 4th plus 1. That's the derivative. And so then we want it at x equals 1. So we're going to plug 1 into this. And it's going to give us 2 over 2, which is 1. So that's your slope. So then we're going to write the equation in point slope form. Y minus pi over 4 equals 1 times x minus 1. Point slope form. Okay? So those are the last derivative rules that we're going to learn this year, actually. I've taught you all the derivative rules now. We have essentially finished derivatives. And next semester, we will be starting the other major half of calculus AB, and that would be integrals. All right, so today you should, just you can work on the extra credit review if you want, and just make sure you're ready for your final.